Alrighty, howdy folks. I think I got just one last aspect to cover in the sequences section, and it's so I'm still in 11.1 sequences. I think I just got about like 4 slides, and we should be done after that with the sequence one. And this is about special limits, as you will notice that. As you're working through some of the problems, find the limit of a sequence and all that from the book, you will see some special kinds of limits. And so I don't want you to panic when you see them. So all right, so here it is. You are likely to bump into something like a limit of sine x over x as x approaches 0. If you recall from Cal 1, this concept of L'Hopital's rule, that can be applied here. So what exactly is the idea there? If we simply plug in x equal to 0, right, then we end up with a sine 0 over 0. But sine 0 is 0, and 0 over 0, there is no mincing words in that one. 0 over 0 is undefined. Okay? So if 0 over 0 is undefined, how do we find this limit? And L'Hopital said, well, the limit of this must equal limit of the derivatives of the top over the derivative of the bottom, right? That's what limit of f of x over g of x is equal to limit of f prime of x over g prime of x. And so we can say take the derivative of the top. The derivative of sine x is cosine x, derivative of x is 1 with respect to x, of course. And so now you plug in x equal to 0. Well, you get cosine 0 is 1, 1 over 1 is 1, and so that limit is equal to 1. But what is important to remember is you cannot apply the L'Hopital's rule willy-nilly at any time. You must have some what are called indefinite forms, right? What are those? Indeterminate forms, not indefinite. Indeterminate forms. 0 over 0, infinity over infinity, either positive infinity or negative infinity in either top or bottom, doesn't matter. And 0 to the power of 0, right? That is also an indeterminate form. Infinity minus infinity, that is an indeterminate form. Okay, so in those cases you can actually apply L'Hopital's rule, and I'm going to demonstrate with 3 more examples how to apply L'Hopital in special cases. Another one, let's look at this. What is limit as x approaches infinity of the quantity 1 plus a over x raised to bx? Well, as x approaches infinity, a over x approaches 0. A is some kind of a constant, finite constant. So a over x goes to 0, and so inside the parenthesis we'll have 1 plus 0 is 1. 1 raised to something like infinity. Well, 1 raised to any power is just 1, right? So the limit is equal to 1. If you say that, then unfortunately that's not true. What? Yeah, I know. Limit of this is not equal to 1. Really, what is it? That's the idea. Okay, so in order to evaluate this limit, we need to do something. It turns out to be e to the ab. What is e? That Euler constant e. A and b are, as you can see, a over x, that a, and raised to bx, that b. So e to the ab is what this limit turns out to be. So I'm going to give you a proof of that. Let y equal this quantity, 1 plus a over x raised to bx. We can say that, right? Cool. Next, take natural log on both sides. Is that okay to do? Can you take natural log on both sides? Yep, that's a fair move. The idea there being, if a equals b, then natural log of a equals natural log of b. Okay, so when I do that, on the left hand side I get a natural log of y, and immediately I applied the law of logarithm that the exponent bx becomes the coefficient of the natural log, right? So I can write this the right hand side as bx times the natural log of 1 plus a over x. Are you okay with this? Cool. Now let's take the limit on both sides as x approaches infinity. Limit as x approaches infinity of the left hand side equals the limit of limit as x approaches infinity the right hand side. Okay, am I allowed to yank this b outside of the limit like that? Yeah, a constant multiple can be pulled outside of a limit. What do I mean by constant multiple? Some constant is multiplying a quantity. B in this case is the constant that is multiplying the remaining quantity, x natural log of blah blah. So that b can be pulled outside of the limit. Okay, and then we have this. Let's look at this and see as to what this quantity turns out to be. Limit as x approaches, x goes to infinity, 1 plus a over x becomes 1 because a over x goes to 0, and natural log of 1 is 0. Infinity times 0 is what we have. What is infinity times 0? Well, anything multiplied by 0 is 0, man. No, man. It's not. So infinity times 0 is actually another indeterminate form. Okay? So we can apply L'Hopital's rule. But before we apply L'Hopital, there's something we need to do. We have to convert this infinity times 0 form into either 0 over 0 or infinity over infinity. Are you cool with that? Infinity times 0, before you apply L'Hopital, be sure to convert that into infinity over infinity or 0 over 0 form. Okay, how do we do that? Can I write x as 1 over x? Let me repeat that. Can I write x as 1 over x? Yeah. So I'm going to say natural log of 1 plus a over x over 1 over x. Now let's ask, what does the top become? A over x goes to 0, natural log of 1 is 0, 1 over a very large number as a limit, that is 0. So we do have a 0 over 0. So at this stage, we can apply L'Hopital, which means we will take the derivative of the top and the derivative of the bottom separately. We will not apply a quotient rule. Be careful about that. When you apply L'Hopital's rule, even though you have a quotient, do not apply the quotient rule. You need to find the derivative of the top and the derivative of the bottom separately. Okay? All right. So is equal to b times. By the way, I think even in the previous problem I did this. I put an L on top of the equal sign. That is to indicate that we are applying L'Hopital's rule as we go from this expression to this equivalent expression. Okay, or this expression. Forget about the equivalent part. And so we have natural log of 1 plus a over x. The derivative is 1 over 1 plus a over x times the derivative of 1 plus a over x itself. Chain rule. The derivative of 1 plus a over x is, the derivative of 1 is 0. The derivative of a over x is negative a over x squared. Okay. Similarly, the derivative of 1 over x is negative 1 over x squared. And now, would you agree we can cancel this x squared with that x squared? And so would we end up with a negative ab times, there's a negative and a negative here, negative ab over negative 1, and so that just becomes positive ab times Now what's this limit of this guy? All we would be left with is limit of 1 over 1 plus a over x, but a over x goes to 0, and so we have 1 plus 0 in the parenthesis, and which is 1, so 1 over 1. Are you with me? Cancelled x square and x square. Negative 1 goes into negative a times. A times, I can yank that a outside, and so I have ab times limit as x approaches to infinity of this quantity, which that quantity goes to 1 as x goes to infinity. And so this just became ab. Cool? All right. Now, what do we mean? How do we interpret this? Could we say this? Thus, as x approaches infinity, right? When we say limit as x approaches infinity, that's what we mean. As x approaches infinity, natural log of y approaches ab. Can we say that? As x approaches infinity, natural log of y approaches ab. Where did I get that from? Well, the very concept of limit is precisely that. When we say limit of natural log of y as x approaches infinity equals ab, please pay attention to this. When we say limit of natural log of y as x approaches infinity equals ab, what we actually mean is as x approaches infinity, natural log of y approaches ab. Cool? Now I have an interesting and important question to ask of you. If natural log of y approaches ab, what does y itself approach? To answer that, it's a good thing to think about this as, okay, what if natural log of y were equal to ab? Okay, in that case, how would you answer that? Natural log of y equals ab. So what is y itself? Well, raise both sides of the equal sign to a power of e, and you get e to the natural log of y is equal to e to the ab. Right? E to the natural log of y equals e to the ab. But e to the natural log of y is nothing but y. Oh, so y itself would be, y would be equal to e to the ab in that case. Or in other words, y would approach e to the ab. Are you cool? All right. So y approaches e to the ab. All right. So what can we say? That means y. What is y? 1 plus a over x raised to bx. So that means we can interpret this as limit as x approaches infinity of y, which is all this, is nothing but e to the ab, which is precisely what we are trying to prove. Okay? All right. So I know that's a bit involved, but if you look at it carefully once or twice, you'll get it. All right? Maybe I should... I didn't ask you this. A silly, simple question. What do you think limit as x approaches infinity of 1 plus 3 over x, the quantity raised to 6x? Piece of cake, right? And that looks exactly like limit of 1 plus a over x raised to bx as x approaches infinity. Yep, this should be e to the ab. A is 3 and b is 6, so e to the 18. End of the story. Okay, cool. What if what is limit of 1 plus 1 over x raised to x? This is an important result. You must know this one. So this turns out to be e. What is that Eulerian number e that we learn? Natural log is a base e. What do you think that e is? That e is actually limit as x approaches infinity of 1 plus 1 over x, the quantity raised to x. Okay. No other definition is as good as that one for e. Okay. Another one. What is limit as x approaches 0 plus of x to the x? That's simple, man. 0 to the 0. Anything raised to 0 is 1. No, man. 0 to the 0 is undefined. And in fact, it is one of the indeterminate forms which prompts us to apply the L'Hopital's rule. Wait a minute. 0 to the 0 is itself undefined. But what is the limit of this? We need to show that it turns out to be 1. Oh, come on. That's what I said. Any number raised to 0 is 1. Now, that's not a good reasoning. Because if I were to ask you what is the limit as x approaches 0 minus of x to the x, then that is not equal to 1. Only in the case of x approaching 0 plus, we can say this is 1. Okay? Gotta prove this. Similar idea. Let y equal x to the x. Take natural log on both sides. Natural log of y equals x natural log of x. Limit on both sides as x approaches 0 plus. And now, when we look at this guy, limit as x approaches 0 plus of the quantity x natural log of x. I should have been careful in putting a parenthesis around this. Right. Then, what are we looking at? What happens to natural log of x as x approaches 0 plus? What happens to natural log of x as x approaches 0 from the right? Do you recall? Natural log of x graph looks something like this. So as x approaches 0 from the right, natural log of x actually goes to negative infinity. And we have a 0 here. 0 times negative infinity. Again, that is an indeterminate form, which means we can apply L'Hopital's rule after we convert this into either 0 over 0 or infinity over infinity. Again, we'll resort to the same technique. We'll write x as 1 over x. So we end up with that. Now we have negative infinity over infinity. And so, yep, we can say apply L'Hopital. And the derivative natural log of x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And so this reduces to limit as x approaches 0 plus of negative x, which is just 0. Okay, do you agree? This reduces to, if you simplify the fraction, you end up getting negative x. What is limit of negative x as x approaches 0 from the right? 0. That's it. So now let's interpret it the way we did last time. That is, as x approaches 0 plus, y, natural log of y approaches 0, which means y itself approaches e to the 0, which is 1. So we say limit as x approaches 0 plus of x to the x is equal to 1. Very important limit. Try to remember this. One last one. What about this guy? What? Okay. We have infinity minus. Can we pull that under one square root? Square root of the quantity x plus a times x plus b. Or, we don't have to. Would we have square root of infinity times square root of infinity, which is like infinity? So infinity minus infinity, that's equal to 0. No. Infinity minus infinity is not equal to 0. It is an indeterminate form. It is undefined, and so this is an indeterminate form, and so we could apply L'Hopital's rule. But, like I said in the previous two problems, we need to make sure that we can write this as infinity over infinity or 0 over 0. How do we do that? Well, that's what it turns out to be, eh? Interesting. And how do we do that? Well, could we multiply and divide by the conjugate? What do I mean by that? Multiply this by both the top and the bottom by x plus square root of x plus a times square root of x plus b thing. Okay, what good does that do? Let's see. Look at the top. I know it looks complicated, but does it look like a minus b times a plus b? All said and done? Yeah. What is a minus b times a plus b? A square minus b square? Right? So, would you agree this simply reduces to x square minus the square of this square root of x plus a times square root of x plus b, which what does it do? It just gets rid of that square root. And so we end up with x squared minus the quantity x plus a times x plus b. Right? Cool. So now if we expand all of that out, that is, what's that thing you guys say? FOIL it out. We get this, or distribute the x plus a into x plus b, and simplify this and factor out, we can factor out a negative x out of this, and we end up with this. The idea there being, again, even from the denominator, we can factor out an x and write like this. Take a look at this. Would you agree with this? Okay, and so when we do that, we notice that x and x we can cancel out, and this reduces to, I went directly there. So the x's go away, and ab over x goes to 0. A over x goes to 0, b over x also goes to 0. So we have 1 plus 0 times 1 plus 0, square root of, which is just 1 times 1 is 1. So 1 plus 1. So we end up with a 2 in the denominator and a plus b on the top with a negative here. Negative of the quantity a plus b over 2 is what this ends up being. All right. So again, we can say the limit of all of this is just negative of a plus b over 2. You will need these limits. Quite possibly what I would do is I would say, all right, what's the limit as x approaches infinity of x minus, and I'll give some numbers for a and b, square root of x plus 3 times square root of x plus 5. Right? You go through this process. Don't just invoke the final result and say, oh, negative of 3 plus 5 over 2, man. I would rather you work through the problem and show all the steps. Cool? Alrighty, that's it.